Okay, then yeah, we studied about this size of the matrix, right? So in this case, we had a 5 different rows, and 2 different columns. So the matrix size is 5 by 2. Okay, then so today we will study how to systematically solve this linear system. Okay, and then last time we mentioned about the 3 different methods that we learned in our high school or middle school, but as I mentioned last time, we mainly use 가감법, okay? And so we basically multiply some equation and then subtract that from the other equations so that we can remove a particular variable, okay? And then we follow a particular order by just removing the first variables first, and then the second in the subsequent steps, and so on. So let me give an example. So given this linear system, we can think of this augmented matrix, right? So these are all coefficient matrix, and these are the B part, which is our constant on the right. And then we always start with the first variable, which is our x1, okay? And then, yeah, we still have different choices of removing x1 from the first 2 equations, or the second or the third equations, and so on, okay? So in this case, we first choose this first equation as a kind of a remover, or it can be viewed as our eraser, and then we erase or remove the first variable from the other equations that appears after this equations, okay? So we pick up the first variable, and then we look at the other equations and then see how much this variable is contained. So in the second equation, it doesn't have x1 at all, so we don't need to remove anything from this second equation. But in the third case, yeah, so it contains like -4 times x1. So this is the part that we want to remove by using our eraser, which is our first equation. Okay, and how to do it is by following this 가감법. And so in order to remove this guy, we just multiply the first equation by 4, and thus this becomes this, and then we just add them together with the third equation, which results in this equation, okay? And then we use this equation in the place of this third equation. So we throw away this third equation and then now use this new equation, okay? So in principle, this equation and this equation will be the same kind of equation, but this one now has no x1 at all, right? So, and then what if we have more equations? So suppose we have 3x1 plus x2 plus 2x3 equals 1. Suppose we have these 4 equations, and then we also remove this 3 times x1 in this equation by using our eraser of this first equation. And in that case, we just multiply this equation by 3, right? And then subtract this from the last equation, okay? And that way we will obtain the new equation for the fourth equation that we have. So this is basically the 가감법 that we studied. Okay, and then yeah, let's think about this equation after removing this part. Okay, and then we can think of the corresponding augmented matrix, which now has the new third equation that has 0 and -3 and 13 and -9. Okay, and then yeah, in this rectangle or this two-dimensional kind of array of the numbers, we can view this process as using this value. We actually removed all these coefficients shown below vertically in this matrix, right? And then accordingly, these equations in the below, they will change accordingly after this guy gets removed. Okay, so this guy will be our only non-zero coefficient, and then all the elements below it will be zero in this case. Okay, so that's basically the process that we followed in this step. Okay, and then given this augmented matrix, we did what all we can do by using this variable or this coefficient. And then now, if we think about this submatrix, which is a sub-rectangle in our augmented matrix, and then we can view that part as also a separate or another linear system, or system of linear equations that we created. But in this case, we do not consider the first equation that we used as an eraser. Okay, and then we consider all the remaining ones except for the first one. But at the same time, among these remaining ones, we removed one variables completely, right? And then if we consider only the remaining variables, and then we can think of these equations, and thus from 3 equations and 3 unknowns, we removed we excluded one equation because we used it completely as our eraser, and then we remove we end up with the 2 equations, but at the same time we also have reduced the number of variables. In this case, we also have the 2 variables in our linear system. Okay, so this can be viewed as like reducing really a big linear system into a smaller linear system, where we exclude one equation and also one variables completely. Okay, and then we do it recursively. Okay, so given this linear system, which is highlighted in the green box, we do the exact same step that we did in the previous step by first picking up this variable, which appears in the first place, which is now our new first variable. And then in this equation, we first do the scaling on this equation. From this equation, we just divide this equation by 2, and then we will obtain this equation, and thus our augmented matrix will now have the new column like this. And then given this subsystem or sublinear system, by using this as our eraser, we remove all these components, all the same variables in the lower part of the equations. Okay, so now this is our eraser, and then these parts will be the ones that will be removed. Okay, and then now we will have a smaller linear system. Okay, after we remove another equation and another variable. Okay, so that way we can incrementally remove the equations and the variables. And then if we had maybe 3 by 3 matrix in our coefficient matrix, which means we have a 3 equation and 3 unknowns, and then after doing this process recursively until we end up with only one equation and only one variable, and then that will be something like this guy. Okay, so by using this as an eraser, we removed this part, and then the remaining equation will be this guy, and then that will be our new third equation, right? And thus this third equation will be really a simple one, which just directly gives us the value of this x3. Okay. Okay, and then the rest of the process will be quite easy, and this will be done by just plugging this value into this equation. I mean, we now go back to the equations in the above, and then just plug this x3 with this value of 3, and then yeah, we will obtain x2 as 12 for in this example. Okay, but in this example, we still use in this case we actually used a 대입법. Okay, so we replaced this variable of x3 in the other equations, right? But I mentioned that we only use a 가감법. Okay, and so let's think about this process as this 가감법 kind of process, and how we do it is to actually subtract some multiple of these equations from this equation and this equation, and that is exactly the same as like plugging this variable of an x3 with this known value of 3. Okay, so how we do it is exactly the same as the previous process. So given this equation, and then we now look up in the above equation, okay, and then remove all these values. And how we do it is by just multiplying -4 in this equation and then subtract it from the second equation. Okay, and then so this was our third equation, and then this was our third equation, and then we multiply it by 4, and then just add it into the second equation, and then we will obtain this new second equation, which is corresponding to the second column. And then now we will have this new column in the second row. Okay, and then also for this first equation, we do the same thing. So we now have this equation, and then we can just simply subtract this equation by just multiplying by 1, and thus we just subtract this part from the first equation, and that way we obtain this. Okay. So if we think about this process again, we all started from this first variable in the first equation, and then removed this variable in all the below equations, right? And then we end up with the smaller one, and then pick up the first one in the first equation again, and then remove all the same variables in the below equations. Okay, and then we do this until we reach the end. Okay, and then once we obtain this single variable and the single equation, and then now we go back, okay, by looking up in the above equations. Okay, so we start with this guy, and then remove all of them. Okay, and then starting with this guy, and then we remove all of them. Okay, now this is the final kind of equation that we obtain, which is just nothing but x1 equals some value, x2 equals some value, and so on. Okay, and then still we can, in terms of its an augmented matrix, it will be having a non-zero value along the diagonal, and then no other values as non-zero values in these other parts. Okay, so this simple, basically our solution, it can be still viewed as this augmented matrix, which has this diagonal element as 1s, and then all the other elements as 0. Okay, so this one will give us just the solution directly. Okay. Okay, and then let's think about this process a little bit more closely. So I mentioned about the process of first removing all these parts and then remove this part, right? But what if we didn't completely remove this lower part? Okay, so for example, so instead of this column, suppose we obtained like 2 here. So this value is 2. So we didn't completely remove this value in the previous step. And then suppose we want to try to remove these values, okay, these values by using this one, okay, and then from this example, suppose we had a 3 here in this case, and then after multiplying by negative 4 and then add it to the second equation, and then this guy will also be multiplied as negative 12 and then add it into these values, right? And so in this final equation, if we had only one variable and then while multiplying it by some numbers in order to remove this particular variable, okay, but since this guy has all the other variables, and then even if so suppose this guy was, for example, 3, and then in this case if we multiply negative 4 here and then minus 12, negative 12, and then it will be added into this value, right? So previously we made it as 0, but if we had this equation having this variable and also another variable, and then even if we made it as 0, this value will be added back or subtracted back into this second equation, and thus this 0 will become no longer be 0. So once we made a 0, but after it may become non-zero values, right? So that's why we first remove all these values in the below of this diagonal part, okay, and then we use this guy and then remove all these upper parts, and that way we remove we maintain this lower part as all zeros, okay. Otherwise these values may become non-zero, so in that case we made our equation more difficult, right? So this is a kind of intuition or our kind of direction of how to solve this kind of linear system. And then once we obtained this solution, and then we can verify if this equation is correct by just plugging them into the original equations. And then so let's study these 3 different operations that we did in solving this linear system by using this 가감법. Okay, so we basically have 3 different operations that we can use in order to solve this equation. So the first step or first type of an operation is called a replacement, and this is exactly the same as 가감법, because we replaced one particular row by adding or subtracting another equations. Okay, so in this case, so given this third equation, and then we multiplied it by negative 4 and then added up into the second equation, right? So this is basically replacing this second equation or second row into a new row, right? So that is called a row replacement. And then the second second type of an operation is really simple one, which is just an interchanging between the equations or rows. So in this case, let me give an example. Suppose we are given this linear system, Okay, so we have a 3 equation and 3 unknowns or 3 variables, and then this will be our augmented matrix. Okay, and then as I mentioned, we always start with the first equation and also the first variable. Okay, and in this case, that value will be this guy. But because it is a 0, we cannot use it to remove these values. So it cannot work as a eraser, right? And thus, our option is to either use this value, right? So in that case, it violates our rules because in this case, we start with the second variable, not the first one, right? But we always want to use or start with the first variable. And then how can we do it in this case? So we simply change the order of the equation. So given these 3 equations, we just pick up some other equation that contains this non-zero coefficient for the first variable, such as this guy and this guy. Both of them will have non-zero coefficient for the first variable, and then we place or change the position of this second equation or the third equation, and then move it to the first one, and then this guy will be positioned in the second row or second equation. Okay, so basically in this linear equation, system of linear equations, it doesn't change the solution even if we change the orders of these equations, right? So their orders doesn't mean anything, right? And so we can freely change their orders, and thus we pick up the second one and then change the position with the first one, and thus we obtain this new augmented matrix. Okay, so this is called row interchange because we switch it the orders of the 2 equations. Okay, and then now we have non-zero eraser here in the first equation for the first variable, and thus by using this we remove these part below this entry. Okay, and so this is corresponding to this second step or second type of a row operation, and then the third type of a row operation is scaling, which is really a simple one as well. So this one is corresponding to let's see. Yes, so we had this. Let's see. Okay, so let's look at this example. So suppose we had, so let me give a new example of having a 1, 2, 3, 4 as the first equation, and then maybe suppose we obtain a 0 here, and then also zeros here by using this as an eraser. So this one may have 2, for example, and then 0, and then 1 and 5 and so on, and then suppose we had 4 and 5 and 1. Okay, so suppose this one is the intermediate augmented matrix that we had, and then in this case we pick up this guy and then remove this value, and we can do it by just multiplying it by 2 and then subtract it from the third equation, and then this third row will be changed into 0 and 0 and negative, it's 3, right? And then negative 9, right? Okay, and then we obtained this equation in the place of the third equation, and then here, in order to obtain x3, it is corresponding to this equation, and in order to obtain x3, we just divided it by 3, right? So in this case, by using this a single equation, we just multiplied it by a certain number, and that number was like 1 over 3. So in this case, we call it as a row scaling. So that is corresponding to this third step. Okay, so these three are the three possible types of operations that we do in order to solve this linear system. Okay, and then we basically want to change this given augmented matrix of this guy. Yeah, originally we had this guy, and then we want to change it into the form of having the diagonal entries being non-zero, and then all zero in this off-diagonal part, or this below part, or this upper part, and then some numbers here. Okay, so we want to change this augmented matrix into this form by using these three elementary row operations. Okay, then so let's study a few new terms. So we see this term of row equivalent. So row equivalent means if we had a one matrix, which will be our augmented matrix, and then we change it by applying some of these elementary row operations. Okay, so by using any of these row operations multiple times, we sometimes do the row replacement and sometimes do the row interchanges and scaling, and then suppose we obtained another augmented matrix after applying some of these. Okay, and then these two matrices are called row equivalent. Okay, equivalent means in Korean 동치라고 했었죠. Okay, so we call these two matrices are row equivalent if we can change one matrix into another by using these elementary row operations. Okay, and then we can think of the corresponding linear system, right? So this one will be augmented matrix of some linear system of maybe x1 plus x2, 2x2, maybe 3x3 equals 4, and so on. And then suppose we also think about the linear system of this augmented matrix. Okay, and then we know this linear system, and then another linear system corresponding to the new augmented matrix. The solution between these two linear systems are exactly the same, right? Because these row operations doesn't change the solution at all, right? So if we look at this example, and then all these operations will not change the solution, and basically the main purpose of applying these row operations is to solve the solution for the linear system of the original equations, right? So these operations doesn't change the solution at all, and thus if the two matrices are row equivalent, and then their corresponding linear systems will have exactly the same solution, right? The solution will remain the same. Okay, and then now let's think about the issue of the existence or uniqueness of the solution. So last time we studied about the three possible cases in terms of the number of solutions in the given linear system. So our linear system will have unique solution, or sometimes it will have no solutions at all, or infinitely many solutions. So these three were the possible cases for a certain linear system, right? And then how can we determine a particular linear system has at least one solution, which means either unique solution or infinitely many solutions, right? Or how can we determine whether the linear system has no solution at all, right? So those kind of types of questions is corresponding to these existence or uniqueness of the solution in our linear system. So last time we studied about this new term of a consistent in case our linear system has at least one solution. Okay, in that case it corresponds to the case of having at least one solution. And then if the solution exists, and then is that solution unique, or the solution is only one, or infinitely many solutions? So that is corresponding to this uniqueness problem. Okay, and then we will study how to determine how to answer these questions by using some of these linear algebraic techniques. And then let's first look at this consistency of a linear system. Okay, and whether the solution exists or not is actually naturally revealed by following this kind of process of row reduction that we studied by using the previous example. So let me show the example. So in this case, let's just follow or apply the process that we learned. And so because it's 0, we change the order between the first and the second equation. And then we remove this part. And then this one will be our corresponding augmented matrix. And so by using this as an eraser, we remove this part. And then now we have a smaller linear system that has one less equations and one less number of variables. And then we pick up the first one in the first equation, right? And then remove this part, right? But in this case, let me ask one question. What if we had, we happen to have 0 here? In this case, what kind of row operations should we do in this case? So we consider this smaller linear system, and then we always pick up the first variable in the first equation, but this guy is 0, right? And so we look at the other ones, other equations, and see if anything, any other equation has non-zero coefficient in the first variable. So this guy has non-zero, and so it's time to do the row interchanges. Okay, and then we can just simply move it to the top, and then move it to the bottom. And then using this now as an eraser, and then remove the bottom part of these non-zero elements. Okay, but anyways, so in this case, both of them are non-zero, so we use this guy as an eraser. Okay, and then remove this value, and thus we obtain this as 0. Okay, and following this process, we first removed all these elements, right? But in this case, suddenly this value became 0. So again, if we follow the process by using this, we remove this value, and then from this linear system, by using this, we remove this part, and then what will be our next smaller linear system? It will be this guy, right? But this guy has a 0 here just by accident, okay? And then now this value. So we now have a one equation after removing one equation and one variable at a time. But after all, the last equation actually had no variables at all, but still we have one equation, okay? So basically we have no variable, but we still have the equation to satisfy, okay? And in this case, this right hand side of the value, this constant value, is actually non-zero. So in this case, we have no way to satisfy this equation, right? Because it is corresponding to like 0 times x3 equals 5 over 2, right? So in this case, we clearly see that it is impossible to make this as true, right? So in this case, we can see that this linear system has no solution at all, right? So this is basically the way to determine whether the system has the solution or not, okay? And then in this case, suppose this one was maybe 3, okay? Suppose this one was 3, and then it will be kind of a standard or kind of a common case where we have only one equation, but still we have one variable. In this case, we can obtain or solve the the value for this x3. And then how we do it is by just dividing it or scaling this equation by 1 over 3, right? And in this case, this guy will be 0, 0, and 1, and 5 over 6, because we just divided it by 3, right? And then in this case, we obtained x3 as 5 over 6, right? And then if we wanted to solve this equation fully, and then we still have to know what the value is for x2 and x1. And then, as we studied, the next process will be to remove these values by looking up in the above, right? By using this value, right? And in that case, after we remove this, and then the second equation will only contain the variable of an x2, and then it will just give directly the value or the solution for x2, right? So still the process remains, but in this case, if we found the row like this, all zeros as a coefficient for the variable, and then some non-zero value on the right hand side, which correspond to the value like this value, this, okay? So in this case, we know that we cannot obtain or we cannot satisfy this equation at all, right? So in this case, we can just stop solving this equation and then just write an answer by saying that, okay, so this equation has no solution, or this linear system is inconsistent, right? Any questions so far? 네. 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 네.
아까 어떤 두 리니어 시스템의 LTS가 로우 이커버전 하면은 그 해시팝이 똑같다고 하셨잖아요.
네.
그 역도 성립.
네. 그러니까요. 네. 그러니까 뭐 가장 쉬운 예는 이제 solution. So what is the solution for this? So it will be 1 and 1, right? So this is a one linear system, right? And then let's think about another linear system of, I'm just writing the solution in this form. Okay, and then we have a new linear system, right? So they have the exact same solution set, right? And then the student's question is, considering their augmented matrix of this matrix and then this matrix, are these two matrices row equivalent or not? Okay, so the answer is yes, because if the answer is yes, we should be able to find some sequence of row operations to make this guy into this form or this guy into this form. Okay. And then let me just give a kind of easier way to make one matrix into the other by using the row operation. So let's use this matrix as a starting point and then do some row operations to make this matrix. Then how can we do it? I just multiply this and -2, and then it will be 0 and -2 and -2, right? And then we can just imagine the exact inverse process of converting the left one into the right one. Okay, I'm just showing the opposite is also possible. So we change the second equation into this form, and then now we just multiply. So this one corresponds to row scaling, right? And then now we multiply the first equation by 1 and then add it into the second row, and then the new equation will be 1 here, and since we have 0 and -2 will still remain as the same, and then -1. So we made this second row in this augmented matrix by using the row operation. So in this case, the row operation that we used is the row replacement, because we multiplied this guy by 1 and then added it into the second row. Okay. So that way we can always change the one augmented matrix into another one by still using the row operation. Okay. Any other questions? Yeah, so related to this example, let me make another comment. So these kind of row operations, so we can imagine some sequence of row operation from by changing one matrix or one augmented matrix into another one. Okay, and then suppose we applied in the first place we applied maybe row interchanges and the row replacement and then scaling and so on, and we can imagine some sequence of row operations to change this guy into another one. Okay, and if there exists such kind of a chain or sequence of row operations, and then these row operations are always reversible. Okay, so it can be always invariable, or we can always make the resulting matrix back into the original matrix. So we can think about it as a kind of a invertible operation. Okay. Okay, so we will study about this much in detail in the later lectures. But please note at this point each of these row operations are reversible or invertible. So we can make move from one to the other and vice versa. Any other questions? Okay, and then let's move to the next subchapter of row reduction and echelon form. So we start with studying a few new terms or new mathematical notion. The first one is really simple: non-zero row or non-zero column. So given some matrix, the row vector is these horizontal vector, right? And then the column is the vertical one, like this. And then if we call it as non-zero row or columns, and then we can first think about the zero column as having all zero values in the corresponding row. So if we had all zeros in a particular row, and then it is called a zero row, okay? And then of course, like this row will be non-zero row, but at the same time, maybe 2, 0, 0, 0 will also be called as non-zero row, okay? So that means if we have at least one non-zero entry in our row or column, and then it is called a non-zero row or column. And then now, in this, by using this notion, we can define a new term called leading entry. Okay, the leading entry. And the definition of this leading entry, is actually it is defined in the row vector. Okay, so non-zero vector can be defined in either column vector or row vector. Okay, so if we consider like this column, and then it is the zero column, or maybe this will be non-zero column. But when talking about this leading entry, we only consider row, okay? And we consider non-zero row, okay, non-zero row, and then we pick up or choose the first non-zero element, starting from, by looking from the left, okay, moving to the right, and then we pick up the first appearing non-zero element. So that is called a leading entry of a row. Okay. So let me give you an example. So suppose let's consider this column, this row. Okay. So again, we consider the leading entry only in the row vector, and in this row vector, what is the leading entry? So leading entry is this guy, -3, because this is the first non-zero element that we see by looking from the left to the right in this row vector. Okay. Okay, and then now we study about this new term of echelon form, or row echelon form. So basically in this subchapter, we are studying some new terms or a little bit of generalized process of the example that we studied in the previous chapter. Okay, so we pick up the first variable in the first equation, and then remove that variable from the remaining equations. So this kind of process can be kind of defined or kind of systematically explained by using these mathematically kind of clearly defined terms. And to this end, for that purpose, we first study about this echelon form. Okay, so given a particular matrix, suppose you're given a particular matrix, and then if this matrix is echelon form, it has to satisfy a certain conditions, and those conditions are these three. Okay, and then these are closely related to how we solved the linear system. Okay, so let's look at these requirements to be able to call a particular matrix as an echelon form matrix. Okay, so the first requirement is that all non-zero rows, and so we consider non-zero rows or 0 rows given our matrix. Okay, and then suppose we are given a particular matrix as in kind of an augmented matrix, and then this one will be non-zero row, right? And then of course 0 row will be something like this, right? And then another non-zero row can be like 0, 2, 1, 3. Okay, let's look at this example, and then we can classify each row as non-zero and 0 and non-zero row, right? And then in this case, this one is not an echelon form because the first requirement is saying that any of these 0 rows, okay, any of these 0 rows should be placed in the bottom part of any of the non-zero rows. Okay, so we basically classify each row into either 0 or non-zero. Okay, and then in order to make this as an echelon form, all these are non-zero rows should be placed in the above part of these 0 rows. Okay, so NZN, yeah, it will not be an echelon form. So if it is an echelon form, it should be something like non-zero, 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 and 0, 0, 0 row. Okay, so we have to have this clear kind of a boundary. Okay, and then yeah, let's first look at the third requirement, because it is a little bit more easier than the second one. So given this matrix, we consider let's change this matrix so that it can satisfy the first condition by just simply changing the second and the third rows. Okay, and in this case we consider the leading entry of each non-zero rows. Okay, again, the leading entry will be this guy in the case of first row, and in the second row the leading entry will be this guy, right? And then for each of these leading entry, we look at the bottom part, okay, vertically for each of these leading entry. And then if all these bottom parts below each of our leading entry are zeros, and then that is satisfying this second condition. So in other words, all entries in the same column, or if we look at this column vertically from this leading entry, and then all these entries should be 0. Okay, so this red part, or these parts should be 0 for every leading entry that we find in the matrix. Okay, so this is actually the form that we try to convert the original matrix into, right? In the case of solving the linear system from the previous example, right? So basically, if we are solving the linear system by using the row operation, we try to change the given echelon matrix, given the augmented matrix into the echelon form of the matrix. Okay. Okay, so that is the third requirement, and then let's look at the second one. The second one is about the order or the position of these leading entries. So we do not care about the other entries below these leading entries. So that was considered in the third condition, but we only look at the leading entry of each column. Okay, and then let's pick up any of them. So suppose we pick up this leading entry in this matrix. Okay, and then we look at the above columns of this leading entry, and then if we find the leading entry of the above columns on the right part or on the same column, and then it is violating the second condition. So Yeah, let me give an example. So we have like this kind of big matrix, and then for each row we pick up the leading entry, and then let me just mark the leading entry as an X. So something like this. Okay. So in this case, it is satisfying the second condition for the echelon form. Okay. And let me give another example that doesn't satisfy this second condition. Yeah, something like this. Okay. So in this case, let me explain why it is not satisfying the second condition for echelon form. So we can pick up any of them, and then suppose we pick up this guy, okay, and then we look at the above columns, and then look at the positions of these leading entry, okay, of the above columns, and then these leading entries are clearly on the right of this chosen leading entry, right? So in this case, it doesn't satisfy the second condition, okay? And then let's pick up this guy. How about this? So for this, yeah, in these above columns, it has these two leading entries, and all of them are on the left side, right? So it is satisfying the second condition, but for all of them, it should satisfy this kind of condition, and that's when we can call it as an echelon form, or that's when we consider this satisfies this second condition. So we should satisfy the second condition for every leading entry. So in this case, this guy will be okay, and this guy will be okay, but this guy is not okay, right? So this violates the second condition. And what about this? So it considers all these above columns, and then this guy, only this guy is satisfied, and also these two are on the right side, and thus clearly it violates the second condition. And what about this? What if this leading entry on the sum of the above column is in the same vertical position? In that case, it is also violating our condition, because the leading entry in the above column should be strictly on the left side. Okay, so in this case, it is also violating. So for example, like this. So in this case, if we pick up this, and then if we look at these rows, and then we find this guy is violating the second condition. So these three are the requirement to satisfy the echelon form. Okay. So intuitively, you can think of this echelon form as a kind of a staircase. Okay. So staircase is a kind of in the positioned in the reverse kind of order. So we can imagine some kind of staircase as like this. Okay. And in this case, staircase will be something like this. Okay. So these are our stairs, and then you guys are standing like here, and then you step up, okay, following this staircase. I mean, we are imagining like the gravity is in the reverse order. Okay, so when imagining this as this kind of a staircase, in order to be able to a echelon form, we shouldn't see this staircase that are too high. Okay, so our leg is very short, so we can only step up by just a one kind of level. Okay, not just two level. Okay? And also, in this case, can we create our staircase? So in this case, so we start from here, and so we have to always go to the right and bottom, okay? But in this case, since we have this leading entry, our staircase should contain all these leading entry. So in this case, something like this, right? So suppose you are here, and then you have to actually be a Spider-Man to just climb this staircase, right? So in this case, it is not a echelon form. Okay. So the staircase should be this kind of a natural kind of shape, and also at each kind of a level of in terms of a height increment, it should be only one at a time. Okay. But what about this case? So so let's see. So in this staircase, which is our echelon form. So this is clearly an echelon form. In this case, suppose you are here, and then you go to the right horizontally, right? But in this case, before we reach the end, we have to move just one unit to the right. But in this case, suppose you started from here, and then you move to the right by the 2 units, right? So in this case, it is okay. So it is okay. So it is satisfying all the requirements of the echelon form. Okay. So even if our leg is short, we have no problem just walking horizontally. Okay, and then let me just relate it into the process of solving the linear system. Okay. So in the previous one, in this example, so it got a little messy. So let's think about this case. So let me just draw the staircase in this case. So we start from here, something like this, right? So this will be our staircase, right? So this is actually an echelon form, right? So we are in the middle. So it was not the end of solving the linear system, right? But this was clearly a intermediate result that we obtained, right? And that is that should be an echelon form, okay? In order, So the part of the process of solving this linear system is involving of making the given matrix into echelon form. But echelon form was not the end of that gives the final solution, right? So we did additional steps of removing these, right? And after removing all these, the final form is actually called a reduced echelon form. Okay, reduced echelon form. So let's look at the requirement of these reduced echelon form. So the reduced echelon form is basically more strict condition than the echelon form. So reduced echelon form is automatically an echelon form that satisfies already all these 3 conditions. Okay, and then it has 2 additional constraints, okay, or requirement. And then the first additional constraint is really easy one. The leading entry, so we still focus on the leading entry, and these leading entries should all be 1, okay? So for all these leading entry, their value should be 1, okay? And in this case, we can make some echelon form of a matrix into, so that it can satisfy this condition. This process is really, really easy from the perspective of a row operation. So let me, so let's see, okay. So let's look at this example. Not this one. So let's look at this example, and suppose we had 2 here, okay, and then again this guy is echelon form, right? But in order to satisfy the first condition for the reduced echelon form, we check these leading entry and see whether they are all ones or not, okay? But if we find not ones, okay, so for this guy is not 1, so it is 2, right? And then we can just simply do the row scaling on this row in order to make this value as 1 by just simply dividing by 2, okay? And then it can be 1 and 3 over 2, right? And then checking all these leading entry, yeah, they will all be 1. So it is really a trivial one. So yeah, that was the fourth condition. And then the fifth condition is a lot more meaningful, and that is also closely related to what we did in the remaining process of changing this matrix into further like a cleaner or like this final form. Okay, so let's look at the fifth condition. So each leading ones, or each leading entry which now is all ones, okay, we now look at the above part, or we look up in the above part and see if any of them are non-zero. Okay, so if all of them, when looking up in the above columns, starting from the each leading entry, and if all of them are zeros, and then they are reduced echelon form. So let's see. In this case, it is echelon form, but for each of these leading entry, and then we look up in the above, right? And then clearly these are non-zero, so it doesn't satisfy reduced echelon form. So these should be all 0 in order to become a reduced echelon form. Okay, so that is corresponding to the fifth part. So fifth part is corresponding to looking up in the above columns from each of our leading entry. Okay, and then back to this echelon form. No, the third one was looking at the bottom part, okay, vertically, starting from all these leading entry, and all the bottom part should all be 0, and all the upper part should all be 0. So in this example, suppose we found those leading entry in our matrix. And then for each of these leading entry, we look on the bottom part, and for this, and we look at the bottom and the upper part. Okay, so all of them except for that leading entry should be 0 along the column vectors. Okay, so that is the reduced echelon form. And if we look at this matrix, no, not this one, the final one that we obtained, let's see, where is it? Oh yeah, this one is one example of reduced echelon form. So we have this echelon leading entry, and then we look up or down, and then all of them are zeros. So that is the requirement of the reduced echelon form. Okay. Okay, and then given a particular matrix, and then we can change this matrix into echelon form by using sum of row reductions. Okay, and then suppose we obtained echelon form. Okay, originally the matrix was not an echelon form, and then we changed it or converted it into an echelon form, and this process is called a row reduction. Okay, we basically reduced really complicated matrix into a simpler form, which is now a echelon form. Okay, so that is called this row reduction. And then we can further change this echelon form of a matrix into reduced echelon form, right? The first half of solving the linear system by removing the bottom part, and that was corresponding to changing it to echelon form, and then we remove the upper part, was corresponding to change this matrix into further into reduced echelon form, right? So you can imagine that given one particular matrix, you can always make it as echelon form and then further into reduced echelon form. Okay, and then in terms of their uniqueness, so suppose you are given a particular matrix, and then now the question that we can think about is suppose we changed it into an echelon form, and then is this echelon form a unique echelon form of this given matrix? And also another question is, we change it further into reduced echelon form, and is it unique given a particular matrix? Okay, so the answer is the reduced echelon form is always unique. So I give you one matrix of 1, 2, 3, 4, 2, 3, 4, 1, maybe 5, 4, 3, 1. So I give you this matrix, and then I ask you, each of you guys to make it as an echelon form, and then further into reduced echelon form. And then if we compare the echelon form generated by different students, and then they can be different, okay? But reduced echelon form will always be the same, okay? Okay, so the time's up. So let's continue the next time. Yep, thank you very much.
그 리듀스드 에슬론 폼이 이런 것도 돼요? 중간에 애들 영이 이렇게 쭉 들어가고.
네, 그래요.
네.
될 뿐만 아니라
네.
그게 아마 좀 우리가 또 예제로 좀 배울 텐데
예.
이제 뭐 1, 2, 3, 4, 5 이제 0, 0, 1, 2, 0, 0, 0, 5 이거를 보면
예.
자 이게 피벗이 여기 있잖아요.
예.
그러면 지금 이거 리딩 엔트리가 엔트리가 지금 보면 이제 여기에 밑에 위에 여기 위에 요놈들이
예.
네. 일단 이게 에슐론 폼인지 한번 볼게요.
네.
에슐론 폼인지는 이 위에 거는 지금 안 따져도 되고 아래 것만
네,
따져도
아래
돼요.
네.
근데 지금 아래 거를 따지는 기준이 이제 이 리딩 엔트리를
네,
기준으로
네.
하는 거죠.
그렇죠.
그러니까 여기는 지금 다 만족을 해요.
예.
네. 근데 예를 들면 뭐 네. 아까 여기가 그러면 완전히 0이 된다.
예.
이것도 이제 뭐 괜찮고요.
예.
네. 그러니까 이게 리딩 엔트리인 것만 따지지 이 위쪽 아래쪽을 보는 게 리딩 엔트리가 아닌 컬럼들에서는 우리가 어떻게 돼도 상관은 없어요.
그러면 리듀스드 그 에슬린 폼에서도 이게
리듀스드 에슐론 폼이냐? 라고
네.
물어본다면 맞아요.
맞아요.
그냥 피벗은 요놈이니까 요놈의 위아래만 보면 되는 거거든요.
아 그럼 얘네들은 1, 2, 3, 4 들어가도 상관이 없어요?
1, 2, 3, 4가 들어가면 잘 봐봐요. 그게
네,
어떻게
그럼 안
되냐면
돼.
네. 1, 2가 들어가면 얘네들은 괜찮아요.
네.
근데 여기가 1이 들어가잖아요.
아
그러면 얘가 피벗이 됩니다. 얘가 리딩 엔트리가 되죠.
그럼 얘네 1, 2가 들어가도 된다는 말씀이시죠?
그렇죠. 그때는 또 네. 그러니까 리딩 엔트리의 오른쪽에 있는 애들은 다 괜찮아요.
그러면 1, 2 들어가도 리듀스드는 안 돼.
리듀스요. 이게 리듀스냐? 이거는 리듀스드가 맞아요. 왜냐하면 어차피 이제 요 리딩 엔트리 위아래만 보면 이건 다 만족을 하잖아요.
예,
다
예.
1이고.
예.
네.
그리고 그 중간에 이런 식으로 폼을 만들려고 하셨잖아요.
네네네.
근데 그게 아니라 얘가 뭐 이쪽으로 가 있다던가 막 0이 들어가는데 이렇게 들어가도 되게 튀었네.
예제를 한번 좀 뭐
예제요?
여기서 한번 써. 네.
그러니까 이런 거요. 이런 거요.
네. 이거는 이제 에슐론 폼이 안 되는 게
이건 그냥
계단이
네.
지금 이렇게 됐다 이렇게 거꾸로 가야 되잖아요. 그죠?
네네.
그러니까 이게 항상 오른쪽으로 가면서 올라갈 수 있는 그게 아니라 이렇게 천장으로 이렇게 올라가야 되기 때문에 이게 안 되고요.
중간에 그게 아니라 그냥 에슐린 폼이 아니라 그냥 이런 식으로 좀 만들면 좋다고 하셨잖아요.
네.
그 풀이하는 과정 중에서
네.
그냥 이렇게 만들어도
어떻게요?
그냥 이렇게 만들어도 풀이하는
네네네 맞아요. 그러니까 그게
예.
사실 우리가 그 연립방정식을 풀 때 꼭 x1을 먼저 제거를 하느냐, x3를 가지고 걔를 먼저 제거를 할 수 있잖아요.
그렇죠.
그러니까 이제 여기서는 그거를 항상 우리는 약속을 하기를 x1 그러니까 가장 처음 베리어블부터 제거를 하기로 약속을 좀 하는 거예요.
그래요. 약속. 약간 관례적인 그런 거예요.
네, 그래야 이게 우리가 알고리즘을 짜요.
네.
뭔가 그러니까 펑션을 그렇게 좀 만들 수가 있거든요. 그 프로그래밍을 할 수가 있어요. 네. 안 그러면 누구 아무거나 잡아서 한다 그러면 이게 좀 약간 골치 아프죠. 네.
알겠습니다.
네, 수고했어요. 네.
첫 강의는 못 들어서 PPT 파일 올라오는 데가 있나요?
네, 이거 블랙보드 접속을 하면. 네.
그 매트릭스가 여러 개 있잖아요.
네.
근데 그 아까 연립방정식 풀려고 뭐 가간법 쓸 수도 있고 이렇게 자리 바꿀 수도 있고 하는데 뭐 이렇게 하는 게 그걸 적용해서 형태가 다르게 돼도 두 개의 행렬이 같다고 할 수 있는 거예요?
이게 행렬 자체는 다르지만 걔 두 개 행렬이 이제 로우 이퀄벌런트 하다. 그러니까 이제
엄연히 말하면은 같다고 할 수 없는 거죠.
없죠.
로우
그러니까 로우 이퀄벌런트는 두 행렬이 그냥 동일하다라는 개념이 아니라 그 행렬이 나타내는 그 리니어 시스템에 해가 이제 똑같다. 여전히 해가 똑같이 유지된다라는 개념이에요.
그럼 아까 해 구할 때 그러니까 reduced 그거 설명하셨잖아요.
네.
reduced 에슐론 그거 설명하실 때 그러니까 결국에 이렇게 1, 1, 1 이렇게 나와야 되는 거니까 그럼 최종 해가 나왔을 형태가 그런 reduced 에슐론이 되는 거죠.
맞아요.
1, 29 뭐
맞아요.
그리고 그 reduced 에슐론에서 원래 행렬로 돌아갈 수가 없고 해를 구하는 어떤 행렬에서 이 reduced 에슐론으로 갈 수 있다 이 말이었어요.
잠깐만 다시 한 번요.
그러니까
네.
모든 행렬이
네.
해를 구하면 어떤 에슐론의 형태로 갈 수가 있다고 아까 했었잖아요.
네네네.
근데 그러면 여기서는 여기로 갈 수 있는데 여기서 여기로 갈 수가 있나요?
네, 그것도 갈 수 있어요.
아,
어쨌건 모든 그 그러니까 로우 오퍼레이션이라고 불리던 그 세 가지의 연산들은요, 다 그게 역변환이 가능하거든요. 그러니까 한쪽에서 이제 반대쪽, 그러니까 이쪽에서 다른 쪽으로 왔으면 여기서 또 항상 반대쪽으로 이제 로우 오퍼레이션을 또 쓰면 이제 항상 가능하기 때문에 그러니까 나누기 3을 하면 그냥 곱하기 3을 하면 원래대로 돌아가고요. 그 로우 리플레이스먼트 같은 경우도 여기서 뭐 얼마를 곱해서 여기다 뺀다. 그래서 또 다른 어떤 로우를 만들었다. 그거를 그대로 이렇게 역변환을 좀 또 할 수가 있어서 원래대로 돌아갈 수가 항상 있어요. 그래서 뭐, 아직 그 설명을 미처 다 이렇게 다음 시간에 좀 하겠지만 기본적으로 어떤 매트릭스가 주어져도 이걸 우리는 에슐론 폼으로 만들 수 있고요. 그 다음에 얘를 또 이제 리듀스드 에슐론 폼으로 항상 만들 수 있어요. 이게 그래서 어떤 매트릭스는 뭐 에슐론 폼이 없냐 있냐 혹은 리듀스드 에슐론 폼이 뭐 존재하느냐 안 하느냐 항상 존재해요. 항상 존재하고 우리는 언제나 이렇게 뭐 그렇게 만들 수가 있고요. 근데 이 중요한 건 그 만든 결과물이 에슐론 폼들은 그러니까 한 사람들마다 다 다를 수 있어요. 근데 이제 리듀스드 에슐론 폼은 항상 똑같은, 그러니까 같은 매트릭스면 리듀스드 에슐론 폼은 항상 똑같이 나와요. 그러니까 이제 뭐 그런 것들을 이제 좀.
근데 아까 해가 없는 게 하나 있었잖아요.
네.
000.
네네.
그게 그러면 그건 해가 없을 때는 reduced 에슐론 폼이 안 되는 거 아니에요?
그게 또 좀 설명을 미처 다 못하긴 했지만 그래서 다음 시간에 좀 또 더 하겠지만 이게 그래서 reduced echelon form이냐를 보면 이제 이렇게 지금 돼 있죠?
네.
그러면 순수하게 이 계단 모양으로는 뭐 오케이예요, 그죠? 두 칸씩 갑자기 올라가는 거 없고 옆으로는 뭐 많이 가도 되고.
네네.
그러니까 이거는 이제 에슐론 폼 2고요.
네.
이게 reduced echelon 폼이냐는 아직 아니에요. 그러니까 여기가 이제 또 1이 돼야 되고요.
네.
그렇죠? 근데 이거 나누기 2 하면 돼요, 그냥.
네네네.
네. 그다음에 그러니까 리딩 엔트리를 보면
그럼 이것도 5분의 2 곱하면
그렇죠. 네,
아.
리딩 엔트리가 요 놈이거든요.
네.
그러면 이제 얘는 또 역시 네, 2분의 5분의 2 곱하면 또 1을 만들 수 있죠. 그러니까 로우 오퍼레이션을 통해서 이거를 이제 리듀스 에슬론 폼으로 만들 수 있어요. 그러니까 이것도 다 이렇게 지우면 되거든요. 이 위쪽으로 또 빼고 해갖고 얘는 이건 아니죠. 이건 이제 리딩 엔트리가 아니니까 이제 얘를 기준으로 얘를 또 이렇게 지울 수 있어요. 그래서 이거를 이제 리듀스 에슬론 폼으로 만들 수 있어요.
네네.
그러니까 해가 없다라는 게 뭐 리듀스 에슬론 폼이 존재하지 않는다? 그건 좀 아니에요.
네.
네.
알겠습니다.
네.
감사합니다.
방금 하려던 질문이 저 질문이었는데 그러면 리듀스드 에슐론 폼도
네.
그 에슐론 폼 그 두 번째 조건에서 이렇게 뛰어넘는 거랑 관계 없다는 말씀이시죠?
다시 한번요.
그러니까 이거 그 에슐론 폼이 돼야 할 조건 그 두 번째가
네.
그 이렇게 한 칸 뛰어넘고 밑에 와도 상관없다고 하셨으니까
네네네 맞아요.
리듀스도 그랑 관계없이
네.
1000, 0100, 0001 해도
리듀스 에슬론
성립한다는-
폼이에요. 네.
근데 해가 구할 수 있고 없고랑 관계없고
네. 그게 그러니까 리듀스 에슬론 폼을 일단 만들어서 네. 또 이것도 또 뒤에 나오겠지만 여기가 다 0000이고 마지막이 난제로가 나왔어요. 이거는 그러니까 방정식이 다 0 곱하기 변수들에다가 equal non-zero라는 값이 나온 거잖아요. 이게 이제 만족이 이제 되지 않는 거죠. 그렇죠? 해가 없는 거죠. 그렇죠? 그래서 이게 reduced echelon 폼으로 만들고 나서 혹은 에슐론 폼으로 만들고 나면 에슐론 폼에서 나온 게 0000 그리고 0이 아닌 거 하나가 마지막에만 달랑 나왔다. 이러면 이제 해가 없는 거예요. 네, 그래서 에슐론 폼으로 만들고 나면 이 방정식이 해가 있는지 없는지를 우리가 결정할 수가 있어요.
그러니까 그러면 해가 있고 없고랑 관계없이 그걸 알기 위해서 만든다는
맞아요. 예.
맞아요.
맞아요.
감사합니다.
네.
네, 알겠습니다.
네, 수고했어요.